My name is Jacob Becker. I'm currently a senior at Winston Churchill High School in Potomac, Maryland, and I'm going to be talking a little bit about my research paper titled, "What is the Role of Dark Matter in the Evolution of the Universe?" So to start with just a little bit of background, but like why it's important, stuff like that. So dark matter makes up 85% of all matter in the universe, so it's a very large percentage. It does not interact with light, which is why we cannot see it. It does not release radiation of any wavelength, so even the non-visible light, which is why it's very hard to detect. So just to get into even more background, the standard model of particle physics is kind of the framework of the universe. It describes the behavior of all of the fundamental particles through three of the four fundamental forces. So these are the electromagnetic force, the weak force, and the strong force. And the odd one out is gravity, which is not included in the standard model of particle physics. So particles within this, these are all the subatomic particles. These are split into two categories. These categories are fermions, which make up matter, and bosons, which mediate these fundamental forces. However, there are two very big problems with the standard model of particle physics. The first one being that it does not account for gravity, which is obviously a very large part of our universe. And kind of because of this, it does not account for dark matter because the main force that dark matter interacts through is gravity. I'm going to get into a little bit of observational evidence for dark matter. So we have not actually directly observed dark matter. We don't have any direct evidence, but we have a lot of indirect evidence of the influence it has exerted on the universe. So we have a lot of direct evidence. I'll be talking about a few of the main points. So first we have rotation curves. So according to Kepler's third law, as the radius of an orbit increases, the velocity of that orbit should decrease. However, we have observed that galaxies have flat rotation curves, which means that the velocity stays nearly constant throughout, which is not what Kepler's third law says should be happening. So because of this, we have deduced that there must be additional unseen mass, which would have to provide enough force to speed the orbits up to what we've been observing. So in this image on the right, this thick black line at the top is the velocity we have observed as the radius increases. Then this thin dotted line right below that is the velocity that is added from the dark matter. And the velocity below that is what we would expect to be seeing based on Kepler's third law. Next, we have gravitational lensing. So this is when light from a distant object gets bent around some mass between the observer and the source of the light. And the more mass that is in the middle, the light is going to get bent more. So galaxy clusters were distorting background images much more than we would expect to see, which means that there had to have been a lot more mass in these galaxy clusters than we were seeing. So this image on the right is actually a great example of gravitational lensing. It shows the light being bent. Third, we have structure formation. So in the very early universe, there were small non-uniformities in density. These grew over time. They condensed into the stars, galaxies, and clusters that we see today. However, the early universe was very hot and very full of light, which means it had a lot of radiation, which would prevent matter from being able to gather soon enough, and we would not be able to have these structures that we see today. However, dark matter does not interact with light or radiation, so it would be able to gather much sooner, and it would be able to create gravity wells, which could then pull in the ordinary matter, and the universe would have enough time to develop into what we see today. And finally, we have the bullet cluster. So this is the result of the collision of two separate galaxy clusters. And the center of mass that we measured using gravitational lensing was different from the center of mass based on the matter we could see in the cluster. So the dark matter spread out more within the cluster while the visible gas cooled down and stayed near the middle of the cluster. So in this image on the right, the pink is where we would expect the center of mass to be based on what we can see, and the blue is actually where we have observed the center of mass to be. Finally, I'm going to get into some of the dark matter particle candidates. So there are a lot of potential dark matter particles. I'll be talking about the three main ones, and all of these are theoretical. We have not confirmed any yet. All right, so first I'll be talking about MACHOs. This stands for Massive Compact Halo Object. These are objects with a lot of mass that emit very little light. This makes them very difficult to detect. So this includes things like black holes, neutron stars, and brown dwarfs. However, these do not make up enough of the total mass of the universe to be a viable candidate. These only make up about 1% of the mass of the universe, while we know that dark matter makes up about 85%. Second, we have WIMPs. This stands for Weakly Interacting Massive Particle. These are theoretical particles. They were specifically created to match the criteria for dark matter. So we know that dark matter has to be cold. So this means it moves much slower than hot dark matter. It has to interact with the weak force, which is where the weakly interacting part comes from. And so the Large Hadron Collider has been used in experiments for many years, and it has not found any evidence of WIMPs, which has led to them kind of becoming less prominent as a candidate. And this picture on the right is of the Hadron Collider, which has been used for these experiments. And finally, we have axions. So the mass ranges for axions are much smaller than MACHOs or WIMPs, which means that there has to be a lot of axions in the universe. So these axions last a long time and they interact with the weak force, which makes them perfect candidates for dark matter. There are currently multiple ongoing experiments to find these axions, such as the haystack at Yale, which is pictured on the right. And these are currently the most popular theory among the particle candidates. So to conclude, we have not detected any of the particle candidates for dark matter, and we don't really have an exact idea for what kind of particle dark matter is. There's a wide variety of things that it might be. And while I discussed WIMPs and MACHOs, axions are the most likely particle for dark matter. And in the future, high-resolution measurements of the cosmic microwave background, which is leftover radiation from the Big Bang, should be very helpful because this would kind of let us know what some of the inherent properties of dark matter have to be.